This is CVPR discussion part 1. I'm talking about Qualcomm specifically here. Shout out to the This Week in ML podcast. He had one of the Qualcomm engineers on, and he was talking about what Qualcomm will present at CVPR. So I'm using this occasion to start my series on CVPR. It is Wednesday now, and next week, Monday till Wednesday, I'm going to be at CVPR in Seattle, attending workshops and presentations, talking to people, things along those lines. So let me talk about what Qualcomm is presenting here in this podcast and probably what they're going to be presenting at CVPR. So there is a paper about speculative decoding. The idea of speculative decoding is to use large language models to kind of pre-select tokens for multimodal models and therefore accelerate inference. The next paper I'm going to talk about is how to use video to infer actions. This is a particular application would be, for example, you have a video camera which is showing how you're doing squats, and then the AI can predict whether you're doing the squats correctly or not. More accurate depth, next paper, third paper, more accurate depth estimation from 2D and 3D. The idea here is that depth estimation relies on various modes, whether it's temporal iteration, whether it's stereo. The fundamental problem here is that you don't have enough parallelization opportunities, and they're trying to solve this because one of the key problems of Qualcomm has always been to do the same thing that AI can do at scale with a limited compute budget, which is what their phones and so on and so forth are exposed to. So the next paper I want to discuss is it's not a paper. I just want to mention the CVPR workshop on large video models and inference from limited compute. I'm not going to talk more about this because I think this is a more, like, all of these problems do affect autonomous driving. Actually, they mention that almost in every paper because the same issue that a phone has is also applying to embodied intelligence in general. Like you have, heavy models, let's say for video inference, that can actually add semantics, but then when you do the actual inference on a robot, on a car, on a phone, the amount of energy you need, the amount of time would not be sufficient, or you just don't have the kind of compute budget to do very good inference. So video stereo data, this is similar to the paper I discussed before, the idea of stereo, capturing stereo, and the parallelization of stereo comes down to a very fundamental problem. This is that when you have two stereo cameras, they typically process information in sequence. So you take the left and the right and you compare and you somehow calculate the depth. What you're trying to do here is do this in one shot and therefore add parallelization. Last time I want to talk about Omnidirectional computer vision workshop. This is a potential workshop I might actually attend because this workshop is actually one of the big ideas that we're working on, which is seeing physics through two-dimensional images. What that means is that if we could have better computer vision models that can infer three-dimensional relationships from two-dimensional pictures and potentially even learn physics. So once I have 3D, I can learn what it means to touch something. I can learn what it means to bump into something. So I can start approaching learning physics. The idea is have end-to-end learned physics from 2D images. This is, of course, just a step towards that. But this is something that we're really interested in also in context of Omniverse and NVIDIA, and of course in the context of the humanoid robot at Tesla. This is not your own podcast. It's June 11th, 2024. This is Krim Telco. For the day, the fund is down 1.5%. The market is up 30 basis points for the year. We are down 10.1%. The market is up 12.5%. We're underperforming by 22.6%. So I want to start this discussion with the paper, more accurate depth estimation from 2D and 3D. So the idea here is that you have a 2D image and you want to estimate first 3 dimensions. So you want to have an estimate of how a 2D image might look in 3D, and then infer from that what it means what depth actually means. So if I take a picture of a plant and then I have it in 2D, I have my pixel space really doesn't understand depth, and then the 3D transformation adds this information, and then I can use that for, let's say, autonomous driving or robotics. Everything that, at least from our perspective, everything that's interesting here is really sort of the path towards a better simulation engine, so we can have images or videos that can be used for learning, or even create a simulation engine that directly teaches robots, let's say, how to grasp a knife, or how to clean a floor with a piece of cloth. All of these things require physics, and what we're trying to achieve here is we're trying to infer three-dimensional physics from two-dimensional images. So what's going on exactly in this paper is to use transformer architecture that takes a 2D image and then learns a 3D representation of the image, and then also infers depth information. Again, this is we're not going to go into more technical details. The paper's in the show notes. I think what's really important here is, again, the path towards a better simulation engine that can use video and learn from video, learn 3D from video. This is, I would say, probably the most interesting angle that we can see for CVPR this year, because robotics is in everybody's mind. The reason robotics is in everybody's mind is actually because we have advances in computer vision, which allow simulation engines to be used for robot learning. And once we pass that milestone, we have opportunities for reinforcement learning, we have opportunities for convolutional neural nets, we have opportunities for transformer architectures to use, or diffusion models. So we can start using all kinds of different models for the planning task that for now we're kind of limited, because particularly reinforcement learning in robot planning is difficult, just because you don't have the kind of luxury to iterate and fail and all of that. Next paper is related. It's using video stereo data, or create video stereo data more efficiently. So the idea here is the following. So when you have video stereo data, which is sort of the state of the art in how, let's say, autonomous vehicles estimate depth, you then have to deal with two problems. One is you have a very large compute, because we're looking at video and images and pixels and all of that. But then most importantly also, it's difficult to parallelize this, because video stereo traditionally works sequentially. So first you look at the left side, then you look at the right side, then you compare, then you put this on a horizontal plane, and then you estimate depth. Now what this paper is attempting to do is use a neural net to do all of this in one shot. So, and do it not sequentially, but in parallel. So this is, in a nutshell, what the paper is doing. Again, we're not going to go into technical details. I think what's interesting about this is that Qualcomm is solving problems for the phone, but this can be also used for autonomous vehicles. The next paper is what they call see a video and then infer actions from the video. What this paper does, I'll give you the high-end example, or the high-level example. The high-level example would be, imagine you're doing, you have a workout, and you're recording your own workout, and the AI is telling you you're not doing the squats properly, or you're holding the weights in a wrong way. And the reason it's able to do that is because they're applying a large language model, or a language model. Actually, it's not a large, but they're applying basically semantic reasoning to the spatial positioning of the video. So in other words, you have the view of a squat, and then you're adding a language model which describes how the squat should look, compare it back with a spatial representation, and basically learn through examples. Of course, this is all data-driven learning, whether that particular squat position is correct, and if it's not correct, it tells you to correct it. So that's kind of the idea here. And I find this interesting because, again, Qualcomm, of course, is working on saving compute budget, because when you have language models, you can't, I mean, you can't use ChatGPT for this on an iPhone or a Qualcomm phone, because it would eat up all your compute budget and energy. But what you can do is maybe have a very low dimensional language model and a very low dimensional spatial model to capture the squat, or to capture the way you lift the weight, and teach you that. And what I find interesting here is, of course, again, look at this sort of long term, when we're building a simulation engine for robots. When robots pick up stuff, you could see that this a model like this being used for training a robot, and then at inference time also the robot could be guided through some sort of semantic understanding of the spatial temporal positioning of its limbs, and learn how to act. So in other words, if we can teach a human how to do squats, then maybe we can teach a robot also how to pick up a spoon. So the workflow here would be that we have a model of how to, let's say, pick up a spoon and stir a soup, and then the robot does it, and while it's doing it, it's being trained by the model to fix its mistakes. So again, if we have a training assistant, sort of a digital personal trainer, well, why can't we have a digital personal trainer for a robot that teaches the robot how to do stuff? So I find this interesting, and I think I would like to dig a little bit further, and also hopefully learn at CVPR where this stuff could go. Next paper I want to discuss is speculative decoding. I think this is just an interesting way to solve compute and memory budget problems. The fundamental idea here is the following. So you have, let's say, an autoregressive model that does, ChatGPT. So it does text, predicting the next token through autoregressive transformer architecture. Now, if you do this with images, you have a little bit of a problem, because you're doing a lot of work and using a lot of computer memory that might not be necessary. Things like symmetries. So if you have a picture of a tree, you really don't have to combine the left lower pixel with the right upper pixel all the time. You can kind of skip a lot. Fundamental idea is that you can use speculative decoding for large language models. So again, you can have several tokens being predicted in parallel, and then just using the right token through sort of what they call a draft model. So this is kind of like, think about it like you have the regular, let's say, GPT, and then you have another model under it which helps predict the right token. Now, this might be counterintuitive. Like, you need more compute maybe than in a regular model, but what you're doing is you're converging faster. And in particular with a large multimodal model, when you're inputting video and voice and things along those lines, the actual token prediction problem becomes much, much bigger. So what Qualcomm is saying here is that you might actually get, instead of 8 tokens per second, you can get 50 tokens per second. So you can 5x the amount of tokens that are generated per second, and then choose from those, and therefore converge faster. So while per second you might have more computer memory budget, you use a lot less time to converge, and therefore you're much more efficient. That's the fundamental idea. Lastly, I want to discuss a workshop that is being proposed, a workshop that I actually might attend, and the workshop is Omnidirectional Computer Vision Workshop. This is, obviously it's a workshop, so I would like to attend it and then talk about it more in depth. But the idea here is really, I think, the canonical problem for simulation now, which is, can we infer physics from 2D? That's the idea, right? And the way we can do this is through some of the techniques that we discussed in the papers here in this episode. So the fundamental problem is like, okay, we have 2-dimensional pictures or videos, and we have to do 2 things. One is we have to replicate 3 dimensions out of 2 dimensions, and then have an understanding of depth, and then maybe going forward have an understanding of texture, and maybe even material composition. So again, if I if I throw a ball onto a porcelain glass versus a glass made out of aluminum, it's going to have different reaction. And those things can be learned end to end, or they can be inputted heuristically. Right now, we're sort of in this twilight zone where we still use heuristic physics models. Synopsys just bought ANSYS for that. And there's nothing particularly wrong with that. We shouldn't throw away all the knowledge that we have, particularly the knowledge in physics and the knowledge in how to digitally express physics. But I think what we could do is try sort of get on the path of end-to-end learning physics from 2D, and these are sort of the steps. I think this omnidirectional computer vision workshop is one of the steps. How, particularly when we have 360-degree cameras, so fisheye cameras, and how to infer physics from those cameras. So hopefully in the future, the Tesla car will not just see all kinds of things, but also learn directly from vision how it can maybe interact with certain objects. So to summarize, this is the part 1 of CVPR. We assume this is going to be very similar to NeurIPS. So we're going to have, NeurIPS, I think we had about 12 parts. This is the first one. So it's actually a preview. So it's a preview of papers and workshops that, inspired by Qualcomm. So shout out to Qualcomm, shout out to the This Week in Machine Learning podcast. I think great work, really useful for people like me to have a sense what's coming, to be able to navigate the conference and learn in advance of what I should be even learning. I think also for new listeners, why are we doing this, going to CVPR? I mean, we're a hedge fund, we run money. Well, there's a couple of reasons. One is we do things a little differently. On our intro deck, we have we don't use no Wall Street, no research. Everything we do it ourselves. So if you want to use a more modern expression, we use that. We use end-to-end learning. We don't use any heuristics. But why is it useful to go to a CVPR workshop for us? Well, number one, we have one of the biggest investments for us is Tesla and its application of AI in autonomous driving, and hopefully in the future for autonomous robots. Now, this might change actually on Thursday with the vote if Musk decides to move all the AI out of Tesla, but nevertheless, that's a whole different conversation, whether he moves the AI out of Tesla and then applies it to Tesla, makes money with Tesla. Actually, for us, we're not being paid for research as investors. We're being paid for revenue and cash flow, and that to me doesn't necessarily exclude the idea that Musk pulls some of the research that they're doing out of Tesla. So back to this paper again, the idea is to learn about computer vision, because computer vision is still the canonical problem to be solved, even in autonomous driving. Yes, planning is important, but you can actually, with computer vision, in particular, some of the discussions that we had here, the 2D, the 3D transformation, you can build better simulators and therefore increase the opportunity for planning. So this would be one, maybe the most important reason why we're particularly interested in computer vision. So let me try to get this point across. This is really important. Computer vision, for some people, they might consider computer vision as solved. Well, object detection works. We have what's it called, cloud representation of the environment. We have the Tesla car can see. What's the problem? Well, listen. First and foremost, what the Tesla car sees is, for now, just very, very raw object, differentiation. So it doesn't even know what it sees. It just knows that there is something. So we can add semantics to this, okay? The something is a person. It's a child versus an adult. Different behavior around children versus adults. It's a school versus a government building. Different behavior around the school versus government building. Semantics could be enormously useful for an autonomous driving car. Second, the big gorilla in the room is simulation. So if we can do better by reflecting 3D data out of 2D images and then learn physics from those images, we can then use that for a simulator to train a robot to do better in simulation. Thank you.